in answering a question on a MCQ, a student either knows the answer or guesses it. Let 3/4 be the probability that he knows the answer and 1/4 of him guessing. 3/4 and 1/4. He knows, and this is guess. Assuming that a student who guesses at the answer will get the correct with probability would be 1/4. Assuming that a student who guesses at the answer will be correct is 1/4. What is the probability that the student knows the answer given that he answered it correctly? Okay, what is the probability that the student knows the answer? He happened to get the answer to be correct. Right, guys? So, first thing is we will have to make ourselves clear with the two steps what we are doing over here. First thing is whenever a person reads the question, he knows the answer. If not, he makes a guess. So it's very clear line that we have this to be 3/4. This is the knowledge on the subject. And this is about getting correct. Of course, he knows the answer means the entire thing is correct, is it not? If he doesn't know, then 1/4, a bit more, I guess. No, that's correct. Anyways, so this is correct. And here, if not, the entire thing is correct. And this is wrong, by the way. Let me write that only. So him knowing is 3/4 and him guessing is 1/4. Him being correct is entire space and him being wrong is 3/4 of the time, and this is 1/4. Okay, if you are clear with this diagram, you're pretty much done. Now, what is the probability that the student knows the answer given he knows, given he got correct? What theorem we have to make use of? Yes, Bayes theorem. We have the outcome. What are the chances that it came from that, right? Bayes theorem. So the formula will be, he knows the answer. He got it correct. Sorry, I'm writing the same thing again. He is correct. And sorry, not, what am I doing? He is correct. Okay, no. He knows the answer. And then he's correct and he knows the answer. Okay, so this is the numerator. So we have the denominator to look something like this. P of knowing the answer into P of being correct when he knows the answer plus P of not knowing the answer, that is guess. Okay, not knowing is nothing but guess. I'll just write guess into probability of him getting the correct when he is guessing. And now we'll write the formula. Probability of a event F is number of outcomes in F divided by total number of outcomes in the sample space. And B given A is number of elements in B intersect A divided by number of elements in A. And now, therefore, probability of knowing when he is correct is equal to probability of knowing is 3/4. And of course, when he knows, he knows. So when he knows and him being correct is 1. Right? I hope you guys made a sense of it. When he knows, it's like being sure of. Of course, you guys can understand at this level with negative marking and all of that, right? So this is 3/4 again, plus him making a guess is 1/4 into, and him being correct is 1/4 when he makes a guess. So this is 3/4 divided by, here the LCM is 16, 12 plus 1 by 16. So if you guys want to, you can do this directly. So this would be 12 by 13. So that would be your answer. Again, please understand the diagram. So first is, see, think in sequence. Basically, it will be opposite of this, right? So him getting a correct answer and he knows. So knowledge will be along your x-axis and him being correct, it will be along the y-axis. Okay, so you can take this as x and y. So it's some shortcut. It's not supposed to be done like this. I don't want you guys to learn like this, but just if you're confused, you can do this. This is x and this is y. And then the formula will go probability of him knowing into probability of him being correct when he knows, divided by so on and so forth. Remember, when he knows, he knows. So there's no possibility of wrong being him being wrong. So in this space, him being correct is 100%. Right? This is basically 100%. And he is wrong when he is making a guess. Of course, he can be wrong. So that's 3/4. And him being correct is 1/4. And rest of it is just simplification and formula.